All right, we're going to go over stoichiometry with equations part 2. This is going to be, don't forget to do your travel logs. So the first thing we're going to look at is the fact that they're chemical reactivity, like chemicals react or can react. But there's a way you can predict what's going to happen. You can predict the product of a chemical reaction. One way to do that is to recognize the general patterns. For example, if you take lithium and water, and you react them together, you get lithium oxide and hydrogen. And if that works, then you should be able to predict the products from the reactions from sodium and potassium, remembering that lithium, sodium, and potassium are in the same group with typically the same reactivities. So a general reaction based on what we just did would be 2 of that element plus 2 water gives you 2 element oxide with hydrogen. And how we know this is there are 5 basic patterns that we look for to help us figure out what's going to be produced. All right, so the first one we're going to look at is a combination. A plus B equals C. It's literally an element or a compound, something plus another something gives you one other something, not 2, 1. You're just putting things together to make one whole thing, right? So in this case, you have magnesium and chlorine gives you magnesium chloride. Calcium oxide plus water gives you calcium hydroxide. You notice how these are compounds, not elements, but they combine to make one thing. They don't combine to make 2 things. It's one thing. And then at the bottom, you have carbon dioxide and water gives you hydrogen carbonate, I want to say. Okay. The next thing we have is decomp. It's the reverse of synthesis. So you're taking that one thing and splitting it apart. So some notable reactions, things that we've seen before, is a chlorate going to chloride and oxygen, or a carbonate going to oxide and carbon dioxide. This is most seen in seashells, creating lime for glass and mortar. All right, so you've got the calcium carbonate going to calcium oxide to carbon dioxide, which, if I switch back right here, look at that. It's very close to that. Oh, sorry. The middle one right there. Very, very close to that. All right. And then, so we have synthesis. 1 gives you 1. Decomp. 1 huge thing splits into 2 things, right? Now we have something called single replacement, where you have an element, and this is very specific, you have an element and a compound gives you the element from the compound and another compound using the previous element. For example, a sodium and hydrochloric acid gives you sodium chloride and hydrogen. See how the positives switch out? So you have a positive switching out with a positive. Now, if I started with a negative, I would have to switch out the negatives. But right now, I have 2 positives. So sodium switches out with the hydrogen, which are positive, or the cations. All right. When we see a change, we know there is a chemical reaction occurring. So in this case, when we see bubbles, something's going on. All right. So there's some rules that you got to know for single replacement. For a single replacement reaction to occur, the replacing element, the one that you start with by itself, must be more reactive than the element it's replacing. And how do we know this? Well, table J and our reference table will tell us this right here. So A plus BC gives us B plus AC, meaning that B had to be, A had to be more reactive or more active than B. So how you say, hey, yes, it worked because A was more reactive than B. Simple as that. Okay, so let's look at this. Sodium and hydrochloric acid goes to sodium chloride and hydrogen. Let's see. since sodium right here is more active or higher up on table J, this is going to follow through. This is going to happen. Like, you're going to see something going on. Now, say we did the reverse, and I wanted to do hydrogen and sodium chloride. Because hydrogen is so low, nothing's going to happen. You're not going to see bubbles. You're not going to see anything. Nothing's going to happen. All right. All right, so we're going to do an exercise now. So you're going to flip to the yellow pages, and we're going to see, and yeah, I don't have the little dude anymore. Sorry about that. It's just going to be this. See the worksheet. All right, so first thing we're going to start out, it's a word problem. It's going to tell you what we're looking for, and then you have to predict the products and write the balanced equation. On top of predicting the products, you're going to, we're going to start adding in the phases, because we've already talked about phases. So, remember using your tables to figure out the phases of said components. In this case, it's pretty easy. It's usually solids with aqueous solutions. All right, so we have aluminum added to a solution of copper 2 chloride. So how we figure this out? Well, aluminum by itself is a solid, and then copper 2 chloride. So when I write this out, I know that copper is going to be the +2 and chloride we know is a -1. So with that being said, a 2 + 2 here, a 1 here, you're going to do the crisscross thing, and we get CuCl2, and it's aqueous because it's a solution. Now we got to figure out what the products are going to be. So remember what I said, you're going to switch out the positives with the positive, and aluminum typically is a positive, so you're going to switch that out with the the copper, so you're going to be left with copper and aluminum chloride. So it should look like this. Now, why did I put a 3 there instead of a 2? Remember, it's copper 2, meaning copper is a +2. Now that copper is by itself, that doesn't matter. But I got to look at aluminum. Aluminum is a +3. So that 3 is up here. Chlorine's still -1. So the 3 goes down there. All right, so I got this much so far. It is going to be aqueous. I checked it with my table. And any chlorides, most chlorides do not have the exception, while aluminum doesn't have the exception. So it's going to be an aqueous solution still. Alrighty then. Now I gotta start balancing it. Well, let's look. Aluminum, aluminum, yay. Copper, copper, yay. Chlorine, oh crap. Chlorine doesn't match up. So there's 3 here, 2 here. I'm just gonna make it even, and I'm going to add a 3 here, because if I multiply 3 times 2, that's 6. So if I do that here, I'm probably gonna want to put a 2 here. 2 and 3 is 6. So my chlorines are good. But I just messed up the aluminums and the chlorines. So my my copper is going to match up. Just adding a 3 here, 2 here. I need 2 on this side. I'm all balanced. All right, so I'm all balanced. Now let's see if it's going to react. I got to look at table J. So here's my aluminum. Here's my copper. It is higher than the copper. So yes, this is going to work, because aluminum is more reactive than copper. All right, phases of products in single replacement reactions. Since most single replacement reactions are run in solution, the phase of the products is determined as follows. For elements, list the normal phase of the element. If it's a solid, a gas, a liquid, right? For compounds, soluble compounds will be AQ, aqueous, while insoluble are the solids. I know it's kind of weird, right? Just remember that. Write it down in your on your reference table if you have to. All right, going back to the worksheets. We're going to do another little one. So cesium is added to solution of iron 3 sulfate. So again, we find the first part. Cesium is a solid. Iron 3 sulfate. So iron is a +3 in this case, because that's right there. And my sulfates are -2. So I've got a 3 here and a 2 here. Here's my 2. My 3 is over here. And look how I had that, the parentheses. Like I always say, the parentheses, make sure you do that. It will save you in the long run. And then it is an aqueous solution because it's a solution. All right, so what does that make? That makes, because I'm switching out these two, iron with cesium sulfate. Okay, well, let's look and see if I need to do any crisscross. Well, cesium is a +1. Sulfate's -2. If I got -2 here, 1 here, 2 goes over here. So there we go. Now we got to balance this puppy out. So let's see. Cesium. Oof, that's not looking too good. Irons, that's not looking too good. Let's fix the irons first. Okay, so iron 2 here, 2 here. Done. Don't have to worry about that. Well, let's look at this. We've got the sulfate. There's 3 here. There's none here. So I'm going to pop this 3 over here. But my cesiums are like way off. 3 and 2 is 6, so all I have to do is put a 6 right there. Pretty simple. We're all done. Now let's check with table J. Let's see, is it going to happen? So here's my cesium up here. Here's my iron down here. It is going to proceed through because cesium is more active than iron. All right, so now we have double replacements, right? Double replacements is instead of having just the element and a compound, you have a compound, gives you a different compound and a different compound. So looking at these colors, you got blue and red with black and yellow, goes to black, red, blue, yellow. Okay. In the double replacement, looking at this, 2 metal ions, the positives, in the aqueous compounds switch places. All right. And as you can see, it should make something kind of solid looking. All right, let's look at this example. If the reaction is run in solution, meaning sodium chloride solution and silver nitrate solution, goes to silver chloride and sodium nitrate, will the arrangement produce soluble compounds? Let's look at silver chlorate or chloride and sodium nitrate. Are they going to be soluble or insoluble? So checking our table, we find that silver chloride is insoluble, aka solid. So I put an S right here. And sodium anything will be soluble or aqueous. Okay. There's some rules though. For a double replacement reaction, just like the single replacement, how do we know what happens? Well, we don't have a table to tell us something's more reactive. No, what we got to look for in the products are 3 things. You need a precipitate, a solid, a water, H2O, HOH, those are both the same thing, or a gas. You got to look for those 3 things, solid, gas, or water, which is a liquid, by the way. All right, so we are going to stop right here for right now. We're going to do the exercise in the next segment. If you have any questions, please don't hesitate to ask me. And I hope you guys have a great day.